great to see you all here this afternoon. Let me apologize for December 9th. I know you all were ready to be here on December 9th as well, but unfortunately that one had to be canceled, and luckily we were able to get Brian Conway to come down today to do this, and it's a great turnout. Brian is with the Arizona Department of Water Resources. He went to work for them back in 1999, so he's coming up on about 24 years with the department. He holds a bachelor's degree from Creighton University. Creighton University, and he has a master's of science in hydrology from University of Arizona. And I had lunch with him today, and we've been talking about some stuff. He's got some really interesting things he's going to show us today. So I'll let him take over, and thank you again for coming. All of the questions you sent me were forwarded to Brian, and he mentioned to me that the last slide that he has all of the questions on there that were sent to me, so hopefully he will be able to answer the questions that you sent me, in particular the ones that are in his area of expertise. So some might not be in his area, and you may not get your question answered, but I think he's going to do a good job of trying to do that for you. Okay, Brian?
David, some standing people. We've got a couple of seats up front.
Well, there's a couple of seats up here if you want to come up, yeah.
So,
Good afternoon, everyone, and thank you, David, for the kind introduction. I apologize about us having to cancel for the December meeting. Unfortunately, some other higher priority meetings came up, and staff were unavailable until today. So today, I'm going to be talking about a bunch of different things. I'm going to be talking about just basic groundwater hydrology. I'll be talking about water management, what our agency is doing. I'll talk about the Tucson Active Management Area, which is the area that SaddleBrooke is in. And then finally I'll end with talking more about just the SaddleBrooke area itself and the hydrology around here. So let's just dive right in and talk about the hydrologic cycle. First, I'd like to say that there's a kind of a joke that we have that whiskey is for drinking and water is for fighting.
Yeah.
That seems to be more relevant these days with all the news that you hear about water in the Colorado River basin states and everything like that. So the water cycle, it can be complex. You know, this is a simple diagram where you have clouds that drops rain on the ground, and some of it's absorbed into the ground and some runs off as runoff. It fills up rivers and lakes, and then it's evapotranspired into to form clouds again, and then you have condensation and you have rain. So just one big cycle. Well, it's really much more complex than that. When you really look at the land and all that stuff like that, you can have evapotranspiration, which we call ET, from trees giving off water. You have sublimation, condensation, precipitation, infiltration, percolation, and finally groundwater flow. So SaddleBrooke gets their water primarily from groundwater, which we'll be discussing later. So on the Earth, only 2.5% of the Earth's water is fresh water. Over almost 97% of it is in the oceans. And of that 2.5% of fresh water, almost 75% of that is locked up in ice caps and the glaciers. And so that's why when you hear about climate change and temperatures rising and ice caps melting, or you hear about sea level rising around the world as it warms up. And then finally you have groundwater, which is about 30% of that 2.5%. And then the surface water, like your lakes and your rivers, is 1.2% of that. And of that 1.2%, the others amount, 69% of that is in ground ice and permafrost, and 21% about is in the lakes, and in the rivers is only 0.49%. So very little of the overall water in the world is something that we can see visually on the ground in your lakes or your rivers. So here's some basic terms. Groundwater, it's one word, it's not two. And you can't see it. You can't look below us and see the groundwater. And like I just talked to you about, less than 1% of all the water on the earth is groundwater. Water is present beneath us in the earth's surface. It's in the rocks, pore spaces, and fractures. And it's 20 to 30 times more abundant than the water found in the lakes and streams. So what is an aquifer? Well, it's an underground layer of water-bearing permeable rock. Rock fractures are unconsolidated materials, such as sand, gravels, fines, and clays. What is an aquifer not? It's not an underground river, and it's not a lake. So groundwater is hidden, and it's very challenging to measure and understand. This is something that we do at our agencies, try to understand how much groundwater there is, how it's changing over time. And when you have wells in the ground, like in this diagram, each well may represent a unique subsurface condition because we can't really see what's going on in the underground of us. We can try to get a picture based on what information was provided from when the drill was when the well was drilled. Excuse me, say that 10 times fast. But even then, those well logs can be poor quality or misrepresented to what's actually happening in the subsurface. And so when we have groundwater wells, we try to understand what they're drilled in, what is the water level for this groundwater well representing. So here's kind of a cross-section of a well. So here's the surface. This is a groundwater well. Here's another one. And these little slits here are what we call the screens. This is where the well has these little slits in the well casing called screens that allow water to flow into it. So depending where this well is screened determines where the water flows into the well when it's being pumped. This right here is what we call a fine grain deposit, such as clay, and that is called an aquitard. So water can't move between these two different parts of the aquifer. This right here is what we call the vadose zone. This is unsaturated area between the soil and the water table, the top of the water table itself. This is where water percolates through and recharges the aquifer. And this is what we call the main part of the aquifer here. So let's talk about an unconfined aquifer. So this is considered a confined or artesian aquifer. So this, because it has a confined layer on it, it is what we call, it's under pressure. So when you drill a well into this, if there was enough pressure in here, this water would start coming out at the surface. That's basically what a spring is. It's an artesian well. It's under pressure, and the water is being forced up naturally, as in a spring, or in this case, in a well. So when this well is pumped, or when you're taking a measurement on it, you're only measuring the pressure in this part of the confined aquifer. This well here is drilled in the unconfined aquifer. So let's show you a picture of that. So this unconfined aquifer is it's the same as it has atmospheric pressure in it, and so it's not under pressure. So when we take a water level measurement in here, we are seeing a measurement of what the water table is at that location. All right, now let's talk about what happens when we pump the well. So we have the water tables right here, and then you get what we call drawdown. So as you're pumping the well, you start getting drawdown that occurs, and then when you stop pumping the well, it'll take some time for the water level to recover and return to its original water level elevation. But over time, as you put more and more wells in, you're going to get more and more drawdown that occurs, and you'll get declining groundwater levels. So here's our neighboring well. So when we pump our well, we get that drawdown right here, this yellow line. This is our area of impact, but then when this well pumps, you get drawdown here. And so when you have lots of wells, they all contribute to the drawdown that occurs. So now you're getting lowering of the water table of both these wells. So I'm sure you wonder what happens when it rains around here. You have Cañada del Oro right around here, and so that's more of a wash. It doesn't flow all the time. But if you go down by, say, the San Pedro River, that flows pretty much all the time in many of the areas, especially in the upper San Pedro there around between Benson and the border. You get groundwater and surface water interactions. And so when we have what's called a losing reach of the river, where the river is flowing, but then it starts to lose its water to the stream could actually go dry in that spot because the surface water is feeding the groundwater system. It's losing surface water to the groundwater. And then you can have the opposite. You can have what we call a gaining stream, where the water table is, let me go the right way, there we go. The water table is feeding the river because the water table is so shallow, it's right at the base of the river. And so there's several reaches of the San Pedro River like that where you have losing parts of the stream where the stream is disappearing, going down into the groundwater when it's doesn't have a high enough flow to sustain the river through there, or you have the groundwater feeding the stream so the river is always flowing in those areas when it's at a base flow event. But what happens when we have wells that are near streams? I mean, obviously when you have washes and streams, groundwater usually tend to be shallow, so there are good places to put wells because you don't have to drill really deep and you have shallow groundwater there. But when you start to pump them, we start to get these, the drawdown, the Kona depression like I talked about. This is what we call the groundwater divide right here, where at this point, this line, this imaginary line, groundwater is flowing this way towards the river itself, and then water is being pulled into the well from the drawdown. But as we start to increase our pumping, we start to have a larger Kona depression, which then causes our groundwater divide to move away from the well and move closer to the river. So we're now pulling more water into our well. Now as we start really pumping that well, we really change the groundwater flow. Oops, hold on. So the groundwater divide's gone. You remember it used to be right about here, and a lot of the water was flowing to the river. Well, now it's gone, and we're now pulling base flow water from the river because this is a gaining reach. And so now the river is going to be impacted by this base flow. And so in the Sierra Vista area, they have to do well impact analysis of wells that are close to the river to see if they're going to impact the base flow of the river. So I work in the hydrology division of our department. I work in the geophysics surveying unit. So we have the field services section and the modeling section. Within my section, the field services section, there's the basic data unit, the automated groundwater monitoring unit, and the geophysics surveying unit, which I manage. Our section provides support in making water management decisions by collecting, analyzing, and interpreting hydrologic data. So our section collects all of the hydrologic data at our agency for the most part. So I showed you some wells that are pumping. Well, let's see what they kind of look like. So this is just a monitoring well. This won't have a pump in it. So this is, you'll see these a lot of times at gas stations where they're trying to monitor if the gas underground storage tanks are leaking. But there's also monitoring wells that are put in to monitor the groundwater conditions all around the state. So you have your drill rig comes out, they drill down, and they put a casing in, and then they have well screening depending on where they want to collect groundwater for the different parts of the aquifer. This is more of a production well. So you have your pump down here. You can have what we call a submersible pump, or you can have a turbine up here that is pulling water out of the bottom of the well. And so the well can be screened in just one spot, or you can have multiple areas where the well is screened. It just depends on the well design and the aquifer system that you're trying to draw water from. So this is what it looks like when they drill a well. I think this sound if I were. Oh, there we go. You can hear it. It's kind of here, but this is the drilling rig right here. This is a well that was being drilled in 2017 up in the Big Chino Basin north of Prescott, kind of near Paulden, Arizona. But these are the cuttings that come out of the drill rig that geologists look at to see what kind of rock is in there, where should we put the well screens when we design this well. And so it's very interesting to better understand the aquifer system. Now this doesn't happen all the time when they drill wells. This is more of a scientific well that was being drilled up there, but still, you can get very useful information when you drill these wells. So here's an example of all kinds of different groundwater wells that our groups see in the state. You have your windmill that was eventually turned into a piston jack that actually is now on a solar panel. So you have three different types of pumping mechanisms here. Here's a turbine that's got a diesel pump on it. They don't have power in this area, so they just put a diesel pump. A drive shaft to run the turbine. This is just a domestic submersible pump. Here's a large agriculture turbine down in Pinal County, and here's another domestic ranch well. And then when those wells get turned, whoops, let's go back. So here's a discharge up from a well. You can see all this water coming out. You can see there's airs in the system, so it's billowing. And it's also pulling water from really deep. It's probably about, I think, 700-800 feet was the depth of water of this well. So you can see that it takes a long time for that water to come back up to the surface. But this is a large production agriculture well down in Pinal County. So I'm going to talk to you just briefly about the three groups in our section, about the type of data that we collect and the projects that we use that data for. Here's a stream flow measurement that they're taking, and then right here they're taking a depth of water measurement. I'll show you a little bit more about this shortly. So the type of data that the basic data unit collects is discrete groundwater level measurements. They go to a well and they take a single measurement. This is done for annual index wells and basin sweeps. They also do site inventories for the GWSI database. So GWSI stands for Groundwater Site Inventory Database. This is the database that you can go right to our website at azwater.gov, and you can access. If you go to online services, there's a drop down. This is GWSI. You can go right in there and it pulls up a map, and you can look at all the wells in the state that our basic data group has measured throughout the years. Like I said, we do stream flow cross sections data on the Verde and Santa Cruz rivers. We do that at the headwaters in the Verde, and then also on the Santa Cruz River down in the Santa Cruz active management area. That's between Nogales and Tucson. That's for our groundwater modeling. We did that. The type of projects we work on, not even with data collected, we do open well hole projects. So if we find out there's an open well casing, our group will go out and put a temporary cap on it and make sure that the landowner is contacted, and then he puts a permanent cap on it so someone can't fall down that. We do a number of reports, hydrologic monitoring reports, open file reports, water level change map series reports. We do site verification for all and upgrades for all of our databases. We have to do quality assurance and quality control on all of our data that we collect. We do calibration on all of our data. We work with outside third parties, such as other water providers, to ask them to provide their own water level measurements to our agency. We work with the U.S. Geological Survey on the National Groundwater Monitoring Network. And then we also help with reviewing online driller applications if needed. So this is a map of all the index wells that the basic data group collected last year. I don't have an updated one for this year yet. But it's about the same amount. So we visited a total of 2,314 index wells. These are wells that they've been going to for a long time, and before our agency was started in 1980, the U.S. Geological Survey did that. So a lot of these wells we took over from the USGS. But you can see this group does a lot of work, especially from October to April. They're out in the field every week when the groundwater levels are at static water levels, which means the water levels aren't changing much because there's not a lot of pumping going on in the fall and winter months for the different areas that they go around the state here. The different colors just represent if it's annual, semi-annual, quarterly, or monthly. You can see those numbers right here. But you can see we go all around the state. And here's the results from last year. When you look from the year before and last year, the larger the dot, the larger magnitude of change. Red represents water level declines. Blue represents water levels are recovering or coming up. You can see there's a lot of red. There's also a decent amount of blue. Just depends where you are and what aquifer that well is drilled in. That point represents. So let's talk about how they take the depth of water measurement in basic data units. So this is a wire sounder. They have anywhere from 1,000 to 2,000 feet of wire on this metal sounder. This is a monitoring well that actually, it's a piezometer. It's got 3 piezometers. So you have your well casing here, but then you have these smaller kind of wells. They're just pipes, but they're screened in different parts of the aquifer. And so they'll come out with their wire sounder. And they have a voltmeter right here that they'll connect to the well and then also to the sounder itself. So when the probe that they drop down this well, when the probe hits the water, it's going to expose wire on it. It'll close the circuit and cause the voltmeter to spike. So he's going to drop this down, and the sounder has increment markings on it every 25 feet. So he has to measure from where he pinches that wire off to where that next marking, closest marking is. So then he dropped it down the well, and then, so watch this right here, the voltmeter. When that probe hits the water, it spikes. And so what he'll do is he'll slowly pull the wire out of the well until it drops from that spike. And so that's where the water level is. He'll pinch it off and take a measurement on it. It's very it's kind of an archaic way to do it, but they're dropping these sounders down in wells that have equipment in it. They could be obstructed. They're not nice sounding tubes. which I'll show you in a minute. Our other group, the automated group, actually usually has much nicer equipment that has markings all the way down, because when those sounders break, it's not going to cost them $2,000 to replace it. They just have to splice a new wire or cut the wire and start from where they have the wire right there and put a new probe on. It's very easy. So here's a measure. This is the headwaters of the Verde near Paulden. They're taking a measurement here just to work on getting base flow measurements up there. They also do the same thing along the Santa Cruz River down in here. Here's a real cool time lapse of the Santa Cruz River that they set up their phone, just did a time lapse on it. You can see just how the river recedes over time. I think this was about 30 minutes. Because he set up while they were doing a measurement. He actually has one that he got from this past monsoon where it's actually coming the other way towards him. It has the beginning of the flash flood coming, but I didn't have that one to grab. All right, so let's talk about the other group in our section, the Automated Groundwater Monitoring Unit. They collect high-frequency automated groundwater level measurements. They also go out and they have to go to each site 3 times a year to take discrete groundwater measurements to make sure the sensor is properly calibrated. They've also collected aquifer test area with the transducers because they can change the duration that the transducers take measurements, anywhere from a few seconds to, they usually take measurements every 6 hours, so 4 times a day. The types of projects that this group works on is statewide monitoring, the National Groundwater Monitoring Network, drought monitoring, ongoing QA/QC, and they publish the same reports as Basic Data does. So this is right from our website. This is when you click on one of the automated sites. And you can see, you can see a lot of really cool things with this. You can see the seasonality that's occurring, but you can also see the downward trend that's occurring as well. This is what the instrument looks like. A lot of them will have this mast up here. This is a GOES Yagi antenna that transmits to satellite once a day. You have your solar panel, and then you have your shelter that holds the equipment in it. So they have 133 active sites statewide. Here's a map of all of the transducers that we have. 88 sites are on this telemetry here, so they can download it once a day. And then each site, like I said, is visited a minimum 3 times per year. They have to do it 3 times a year to download the data off of it, because any data that's uploaded through the telemetry get verified first by downloading the data and making sure there's not any anomalies or the sensor's not broken. And then if that happens, it'll get overridden with the new data. You can see these are located throughout the state as well. The wells that we use have to be unused and not equipped, and so we're kind of hampered by where we can put these. Usually, we try to find areas that are important to us, but if we can't find wells in that area, then we have to work with what we have, basically. So this is like a typical setup. So you have your monitoring well here, and then you have your equipment that's just it's stored inside. This is an all-in-one unit, so you have your transducers all at the bottom of this cable, and then this is your data logger right here. And so we connect the laptop to this to download it. This is a different setup. This is our data logger right here. This is our radio that transmits, and this is the vented cable. Because all we're doing when we're measuring is we're just measuring the change in pressure, basically, and then that pressure is converted into change in water level. So like we just saw the measurement before, he's going to come to the site and drop his probe down in there, and you can see this one actually looks like a tape measure. It's got markings every 100th of a foot. And unlike the other one, when this one hits the water, it actually makes a an audible beep on the device itself. So you'll hear it here in just a second. Hear that beep right there. So when that first hears that beep, that's where he'll pinch it off and he'll look at the measurement and see what it is, and then he'll write it down in the book here. So let's look at what the value of high frequency data is. So these green dots here are just manual measurements that are being done. This is the actual transducer. You wouldn't know that you have this large seasonal swing that's going on without the transducer. If you're just coming out once a year to take a measurement like they do, I mean, they can see trends, but they can't see the seasonality in it at all. So this is definitely the value of having a transducer in there that allows us to see any terms of short-term seasonality, or if a pump was turned on nearby, something that's affecting this. Here's another great example. This is up in the Big Chino wash flows right next to this site. And in the monsoon, the wash was flowing, and you can see, look at this. We see an immediate response in the groundwater, because depth of water here is only 19 feet. And so that surface water interacts with that groundwater very quickly, and we see this this recharge pulse from this runoff event. Without a transducer, we wouldn't know that's happening unless you just happen to be out there taking a measurement shortly after. So finally, we'll talk about my group, the Geophysics Surveying Group. The data that we collect is satellite interferometric synthetic aperture radar, or INSAR data. We use this for monitoring deformation around the state, primarily land subsidence. Land subsidence occurs when we pumped out too much groundwater, or if oil was extracted out of the ground, or some sort of ore. Any sort of material being taken out of the ground can lead to subsidence. We also do drone LiDAR and digital elevation models. We use microgravity data to measure the change in mass of the groundwater in the subsurface. So we do this in the Phoenix metro area and the Pinal area, and then the USGS does it down here in the Tucson area. And then we also collect survey-grade GPS data for highly accurate location information, such as latitude and longitude, and more importantly, for elevation data. The projects that we use all this data for is for subsidence and earth fissure monitoring, change in aquifer storage, depth of bedrock modeling, water and storage estimates, specific yield estimates, survey grade elevations, the USGS National Groundwater Monitoring Network. We publish reports the same, just as basic data in the automated groundwater monitoring group. And we do a lot of presentations at a conference and different meetings related to subsidence. Here's what our gravity equipment looks like. This is the U.S. Geological Survey's instrument, and then these are ours. We'll set up on a well or a benchmark, and we'll take measurements every year, every other year. It just depends what the project is. And this will tell us how much the change in storage of that mass in water occurs. We've been doing this in Phoenix since 2002. In the Pinal AMA since 1999, and the USGS has been doing it in Tucson since 1998. We also collect gravity data to model how deep the bedrock is to get basin geometry, and then also we can calculate how much water is in storage for these basins. A lot of these projects, the last one's been done more in rural areas. So here's a 3D map of the depth of bedrock for the Wallapai groundwater basin, which is from Kingman north towards Lake Mead. You can see with the gravity data we can model, we see how deep the basin is, and we can see the geometry of it, and then how much water may be in there for future use. This is a change in aquifer storage in the Phoenix active management area between 2009 and 2014. The blue represents increases in change in storage, and the red represents decreases in change in storage. So like I said, you can get subsidence. So if you think of kind of like a bowl of Rice Krispies, and you pour your milk in, that's our aquifer system. Instead of using a spoon, you're going to put a straw in there. This straw is your groundwater well. Well, as you suck out that milk, and you suck out a lot of it, those Rice Krispies will start to compact in the bowl and will start to rearrange. That's exactly what happens in the subsurface, where you get your wells are here, here's your water table, they start pumping, and over time, they're pumping more than what is naturally or artificially being recharged into the ground. Your water table starts to drop. And so what happens is that these fine-grained sediments start to drain and compact, kind of like the Rice Krispies did in the bowl. And so now they're thinner, there's not as thick, and so what happens is those pore spaces that were being held open by water pressure are just air, and so they collapse because the air can't sustain all this underlying material on top of it, and so you get subsidence. This ground is dropped from here to here. Now you can get cyclical subsidence, seasonal subsidence and uplift, where you have recovery, when the wells aren't being pumped in, but over time you still get a downward trend of subsidence, and also with the water table. Now with subsidence, we get what we are called earth fissures. You might have heard about those. They tend to get all the press because you can see them. Subsidence you can't really see. You don't even know it's occurring. There's over 4,100 square miles of subsidence happening in Arizona. But when those earth fissures open up, they make the news. So how does an earth fissure occur? Well, it starts out as a hairline crack in the subsurface, and it happens from differential compaction. They happen in areas where there's shallow bedrock, where the material can only compress so much right here, but it can compress more here. And so you get these tension cracks that form in the subsurface. So here's your hairline crack. You don't even know it's there. But over time, as you have rain and it starts to percolate down, it starts to open this up and pothole it. So you start to have a pothole. Now that's another easier way for the water to get into this hairline crack. So over time, that water gets in, and you have a large rain event, it'll just rip open this hairline crack and make a very large crack. You have eventually vegetation growing out of it because it's a great place to trap water. So this is us out surveying. This is a benchmark in Wilcox that we recovered. We found it back in 2018, I think, and we hadn't been last surveyed since 1969, I believe, and so we discovered it subsided almost 10 feet since that last time it was surveyed. So let's real briefly just talk about INSAR. We need to have 2 satellite passes to be able to look at the radar data. So what happens is that you have a satellite up in space, it beams its radar beam down. Some of it just deflects, but the majority of it comes back to the satellite. And then you have your second pass that does the same thing. Well, any sort of deformation change on the ground is going to be captured in that signal, because now the satellite is farther away from the ground in this than it is here. And so that changes the change in the radar signal that we're able to process. So these are all the subsidence features we've identified. There's more than 30 of them. And it's greater than 4,100 square miles. You can see all these different features. Here's Tucson right here, Wilcox, Douglas, Bowie, San Simon. A lot of these we knew about. There's a lot of historical reports before our agency was even formed in 1980. And so we knew about a lot of these, but we didn't really know the shapes of them, because when you go out and take a single discrete point with the GPS equipment, it's just a point. You're having to infer what's happening between the points. Whereas the radar data, we're getting a pixel every 15 to 30 meters over 100 kilometers by 100 kilometers, or even bigger than that now with the newer satellites, or even higher, larger footprints. And so we will see large areas. A lot of stuff out here we didn't even know was occurring until we started using the radar data back in the early 2000s. So what happens to the data? Well, I told you kind of already, it gets published in reports, and so our department does an amazing job taking our data and putting it on our website, whether it's in reports, or this is the actual GWSI web map I was telling you about, that you can zoom in to look at water level changes over time. All this data is used for internal and external decision support, groundwater modeling, mitigation, and planning projects. So here's Arizona water use by source from 2019. So 36% of our water is Colorado River water. That's changed a little bit now that we're in shortages. 5% is reclaimed, 41% is groundwater, and 18% is in-state rivers such as the Salt River and the Verde River. Here's our water use by sector. So 22% is municipal use. And, this is the water providers providing water to your homes. 72% is agriculture use, and 6% is industrial use. So when our agency was formed in 1980, we had the 1980 Groundwater Management Act. So that formed active management areas, all these different active management areas. And this past November, the Douglas Irrigation Non-Expansion Area became an active management area. And there's actually a new irrigation non-expansion area up here, in just north of Kingman. Well, it's part of Kingman, and then north towards Lake Mead, called the Wallapai Valley irrigation non-expansion area. So let's talk just briefly about an AMA. They all have management plans. They contain conservation programs, the regulatory requirements, and the effective dates for each AMA. Each AMA is different. They all have different goals and requirements. Right now, we're working on the 5th management period, which is from 2020 to 2025. We're going to complete that for all 5 of the AMAs. Recharge is a great project that's been going on for some time. There's 101 recharge projects in Arizona. So they take either Colorado River water and recharge it, or they'll take your treated wastewater and recharge it. And so they can be recharged in surface basins where they get put in the basins and they slowly percolate down to the groundwater. They can get put in what we call ASR wells, aquifer storage and recovery wells, where they're injected into the well in the winter and then recovered in the summertime. But basically, it's storing water underground for future use. So let's talk a little bit about the Tucson Active Management Area. So here's our boundary of it here. So the Tucson AMA has a goal of achieving safe yield by 2025. Safe yield means that we're not pumping more than what is being artificially or naturally recharged. In the Tucson AMA, you have to have a 100-year assured water supply certificate to build new homes. So you have to prove to our agency that you have this. You have to come to our agency to prove that you have this. And there's been times where a consultant will come in for a water provider or a developer and look at their model and like, your assumptions are way off. They need to be more in line with our model. And it turns out that they can't build as many homes there. They have to scale back a little bit. There's conservation being done. They're utilizing reclaimed water. And there's a number of recharge projects. So here's SaddleBrooke, just so you know, right here, this star. So Tucson does have some science. It has been occurring in the Tucson AMA for over 30 years. This is the feature itself. This is kind of down by the air base in the downtown area. This is what we call kind of the central well field area for Tucson water. But this land subsidence here has decreased substantially over the past 10 years, and this is due to groundwater management and recharge. So remember that this is the feature right here. Well, this is when our first data set of INSAR goes back to the 90s. So you can see there was a feature here closer to the airport, and then this feature is still there. But look at the change in rate. The rate is almost non-existent now. It's very hard for me to see the subsidence feature anymore with just 12 months of data. It usually takes 18 to 24 months to even see it. And this is all due to groundwater management and recharge by Tucson Water mitigating this. So again, here's that subsidence feature. So what Tucson Water did is they put their Colorado River water out in Arrow Valley and recharged it. You can see direct correlation, opposite correlation between the blue line is the central well field. You see, look at the drop in pumpage that has occurred out there in the central well field. So water levels have really recovered out there. Subsidence is diminishing, and they're using their recharged Colorado River waters they put in the ground and recovering it out there. So here's our SaddleBrooke area. This is zoomed in. It's located in the northeast corner of the Tucson AMA. The water is provided by the Lago del Oro Water Company. And you have a 100-year assured water supply certificate. And if you don't believe me, there it is. You can't see it on there, but there's actually quite a few of these because there's been different developments that have gone in out here. Now, talking with David at lunch, he said there's other developments going in this area. They have to have a 100-year assured water supply to be able to build. So rest assured, since they're in the AMA, they have a 100-year assured water supply. So there's a question about snow and rain on the Catalinas and how it impacts the aquifer that David provided me. So I contacted the Pima County Regional Flood Control District and got a bunch of rain data for the rain gauges out here. These are all the rain gauges around this area. Here's Cañada del Oro, right here, this blue line. So these all feed this wash and also will contribute to recharge in the aquifer, the snow and the rain. So we're going to look at the Oracle Ranger Station gauge first. I'm going to show you all these just so you can see what they look like. So this data only goes back about the mid-80s, but it's 35, 36 years worth of data. And people ask, well, is the rainfall increasing or decreasing? And as I'll show you, for the most part, the rainfall is staying pretty consistent. It's either flat or a slight increase or a slight decrease. Some of these are missing data sets in here, but for the most part, these are complete data sets. You can see the average for this is 13.8 inches. Let's look at the Pig Spring one here, right here. You can see this one has a slight upward trend, and it has an average of 17.5 inches, which is what we would expect to have a higher rainfall amount in the mountains. Here's a SaddleBrooke one. No, that's wrong. Oh, sorry, Cherry Spring. This one's flat, not much change at all over time. An average of 14.7 inches. The Rancho Solano one, that's right on Cañada del Oro. 14.4 inches. This one has a slight downward trend, but really not much at all. We'll look at the SaddleBrooke one, which is just right down the street here. Its average is 12 inches. And then finally, we'll look at the Dodge Tank one. Actually, there's one more after this. Average of 13.1 inches, but it does have an increase in rainfall. And finally, the Golden Ranch one, 11.3 inches. And this one also has this slight upward trend. So here's all those on the map, so you can see what the average rainfall is for all those different gauges. You see higher amounts up in the mountains and then kind of lower down at the flank of the mountains. So here's a map that shows the average. I summed all these 7 rain gauges, and so all 7 of them, this is their average. This is their average for all 7. An average of 96 inches a year for those 7 rain gauges. So like I said, the groundwater, the water source for SaddleBrooke is all from groundwater. So here's SaddleBrooke again. These are the index wells that our basic data goes out and measures. These are the 4 closest to this area. So I'm going to show you the hydrographs that show the long-term groundwater level changes for these. So we'll look at this one first, 12 UBC. This one hasn't been around that long. It looks like it's a new well they just added. It has a downward trend. The depth of the water is, almost 800 feet. And it's not dropping that much. It's dropping, about a foot a year, which is not very significant at all. We'll look at this other one on the northwest here, just off of 79 northwest Morrill Junction. You see this one, had some declines, had a recovery period, and then it's kind of been dropping ever since. This one also isn't dropping very much. It's dropping about a foot a year. And we'll look at this next one, just outside SaddleBrooke. You see this one, it has some swings in it. We have a drop and then a recovery period, and then again we have another drop, and we have recovery and then it's dropping again. But this one's not even dropping a foot a year over the past few measurements. And finally, we'll look at this last one, just south of SaddleBrooke. It was pretty flat in the 80s, and then you start to have your decline going on. So that's pretty much it. I just want to close on this kind of what happened when the Groundwater Management Act of 1980 formed. You see, this is when it was formed, and you can see that our water use in acre feet has dropped, even though our GDP, or gross domestic income, and our population has increased substantially. So we consider this a large success at our agency. Obviously, active management areas, these are in active management areas for the most part, because that's where the bulk of the population sits. It's in the more rural areas is where there's not any management that's going on. So as long as you're putting well to beneficial use, your water to beneficial use, you can pump as much as you want. All right, so I will show you the questions that David was sent. So how should SaddleBrooke plan to reduce water usage short-term versus waiting for a state mandate? Ornamental grass, water harvesting. Obviously, when you have a home, your outdoor watering usually takes up the bulk of your bill. Whether it's filling a swimming pool or watering your grass, especially in the winter when you overseed with winter rye, you have to water that grass a lot for it to come in, to germinate, to come in right and seed right. Then you can scale back the water a little bit. But a lot of your outdoor watering is the bulk of your watering of your home. Now, if you have xeriscape, drought-resilient plants, native plants that have lived in the desert, they're still out there right now, and they don't get drip irrigation, that's obviously going to go a long ways with reducing your water use. Low-flow toilets and things like that, checking for water leaks. We all can play a role in reducing our water use. In terms of a water provider or water agencies, one thing they can do is they can recharge their treated wastewater, their effluent, whether that's putting them to use right on the golf course. There's a lot of golf courses that use reclaimed water to water their golf courses. Even cities use reclaimed water to water plants, along roads and stuff like that. We see purple boxes, irrigation boxes, which is the color for reclaimed water, all over the place, and especially in new developments in Phoenix. And I'm not sure if that's the case here in Tucson. I'm not as well versed on that. But using reclaimed water in San Diego, they're drinking reclaimed water. The water that we put to recharge in a lot of areas, it's the highest grade, and you could actually drink it. But we're not doing that. It's not direct to tap yet. In my lifetime, who knows? Maybe that will eventually happen. But if they're recharging the aquifer with reclaimed water, we're using every drop, basically. You lose a little bit to evaporate, it's going back down to the ground, and it will be recovered later. I think I answered the direct role of rain, snowfall, and sand catalyst, but that is what is recharging the aquifer. That water comes down in runoff and goes through the stream, through Caño del Oro, or just, through the desert and percolates down. It takes a while for it to reach the groundwater, but that is what recharges your aquifer, is the rainfall and the snow. Unless they're doing artificial recharge as well. This next one, I can't really speak on this. This would be more of a question for Arizona Department of Environmental Quality, would be my guess. Can I provide a comparison of composition of water source in the aquifer and the river? This is also outside my expertise. At our agency, we don't do water quality. And then how does the state water rights differentiate between agriculture uses versus housing or other uses? Does one have a priority over the other? No, they don't. They're all the same priority. Who is responsible for feasibility studies? We don't do the feasibility studies, so that would be like a developer or something like that. That would have to do those studies. Have I observed brown cracks due to water depletion in our area? No, I have not. There's no subsidence occurring, so we wouldn't expect to see earth fissuring. You can get what we call giant desiccation cracks, which is a naturally occurring phenomenon from the ground wetting and drying. So as the ground wets and then dries, it dries out, which forms these cracks. They can look like earth fissures, but they're not. The issue of desalination of water and transporting via pipeline, it would help our water storage. That is currently being discussed, of putting a desalination plant in the Gulf, in Baja, Mexico, and piping that water north up to the CEP Canal and transporting it that way. I can't speak to this about SaddleBrooke having hard water in other districts, and I don't know the best time of water filtration system for the situation. I'm sorry. Do they still have the GRACE satellite or something similar measuring the world's aquifers? Original GRACE findings seem to find a frightening depletion of large aquifers, which I understand take many thousands of years of replenish. So the GRACE satellite is a constellation of two satellites up in space that, as they get closer and farther together to each other, that's measuring the changing gravity on the Earth. Kind of like what I do with microgravimeter on the ground, but it's a very low resolution. So 1 pixel is something like 300 miles or something like that. So yes, the GRACE is still up there. It's called GRACE FOs, GRACE follow-on, and it's still providing data. And there's, I read reports and stuff about it all the time. In terms of looking at, Arizona, Metro Phoenix would be covered by, I think, half a pixel or something like that. So it's not very beneficial. But looking regionally, through the whole Southwest, yes, it's great for doing something like that. Can I specifically describe the SaddleBrooke domestic water trade-offs in our dedicated guaranteed water supply? Well, I think I kind of answered that one too. The Lago del Oro is your water provider, and they have a 100-year assured water supply. So that's it. I'm open to questions. I think I have about 2 minutes left. No, I'm kidding.
And I got the door open for you to take off. What is microgravity?
So microgravity is where it's measuring gravity like 10 to the negative 90. Very small scale. And so we have a sensor in there that measures gravity at that very small scale. It's called a microgal. And any sort of, it's kind of like surveying with GPS, but we're just using gravity. So that change in gravity, we use some math, and it tells us how much that mass, so you think like a slab of water in the subsurface, it's just telling us how much that slab is changing in thickness of water over time. That's all it's doing. It's not telling us how much water is there, it's just telling us how much the thickness has changed over time. That's why it's called change in aquifer storage. Yes, ma'am?
Would covering the CAP ditches help with our water supply? Aren't we losing a lot from evaporation?
We have but they do a lot of maintenance on them, and so it would take a lot of work to do that and be very expensive. I know that I've heard people talk about, well, put solar panels on it and stuff like that, but it's just not feasible. Yes, sir.
When I first moved here in 2005, I was told that there's an aquifer under Tucson about 1,600 feet deep.
Yeah, I mean, the water goes pretty deep. I'm not, it probably varies on how thick it is.
And the point was, we don't have to worry because there's big water pressure way deep.
Yeah, I mean, there's a good amount of water in the Tucson Basin. How much is there? I can't tell you. Yes, sir.
Two questions. One's more political than the other, but you talked about fighting over water. It's my understanding that they're reducing the amount of Colorado River coming into Arizona. Can you speak a little bit to that? And secondly, California uses a lot more of the Colorado River water than we do. And I understand they're dumping about 80% of the rainfall back into the ocean instead of storing it in a deep well somewhere. Can you address that as well?
So the Colorado River, we are in a tier 2A shortage. So Arizona was the last one to the table in the 70s to get Colorado River water. In order to get that, we had to agree to be the first to take the cuts and the most cuts. And so since as Lake Mead drops to certain elevations, like 1075 elevation was the first shortage. As it drops below to different ones, we take more and more cuts. So I think right now we're at 21% of our allotment that is being cut. It's mostly affecting the farmers. The municipalities are not being affected by it, but as it drops more and more, it's going to, we're going to have to take more. And there's the Secretary of the Interior and the Bureau of Reclamation Commissioner wants states to leave 2 to 4 million acre feet in the water, in Lake Mead. And so they're not forcing us, but they want us to the lower basin states, Nevada, California, Arizona, to come to agreement to try to leave more water in there. And we've been doing, the states have been leaving more in there because they knew it was dropping. And as the lake dries out more, it's going to drop even faster because it's got less of an area to drop into. It's more in the canyon part versus the more spread out part. As your other question with California, I can't really answer that, but I mean, if you can capture your rainwater, that'd be great. Just need to develop something, the infrastructure to do it. Yes, sir.
Before moving to SaddleBrooke, I lived in Florida, and they tell us there in Florida that the rainwater, because of the relatively high water table, the rainwater took only 7 years to actually physically become incorporated in the water table. Do you have a feel for how many years it takes here in Arizona?
I mean, it depends how deep the groundwater is.
Right.
The material, the porosity, all that stuff. So I can't answer that.
Yeah.
I mean, it takes years. It takes a long time.
Hundreds of years here?
Not hundreds of years, but it takes a while. It takes a while. I mean, it depends how deep the groundwater is. If the groundwater is 1,000 feet, it's going to take a long time to get down there. In the back.
Yes. We have this 100-year, I would call it guarantee, but whatever you want to call that. When was that made? And as things have changed, probably, I don't know when, did they reassess that? Because I continue to see more development. I don't know, do the farmers have to have something like that too, or can people just start getting into the same aquifer we use, and they're going to be using, kind of poaching it or whatever, or sharing it, and that's going to affect us too. So really, how good of a guarantee is that?
I'm going to plead the fifth on part of that, but so when someone comes, so let's say there's a new development that's going to come in here that's not part of this 100-year assured water supply. So when they did their 100-year assured water supply, that's set in stone. So if a new one comes in, they have to take in consideration all the other 100-year assured water supply certificates in that area. So if you actually go to our website you can pull up and assure an adequate water supply map. It'll show you all the certificates in all the active management areas. And so when the new one comes in, they have to consider all those water uses that are being used, and it has to be figured into their determination as well.
But I mean, when did ours get certified?
Yours has been, I think the date was like the late 80s, is what I remember. But there's been more than one. There's been numerous ones because there's different like lot numbers and stuff like
Okay,
that.
so when they expand to different areas within SaddleBrooke, like if they choose to.
Yeah, they have to come back in and get a new 100-year sure water supply.
Certified?
Yep. In the back.
Yes, thank you. So your graph showed that the commercial human use is about 6% for homeowners and everything. My question really is, and I don't know if you can answer this, but since 72% of the water use is for irrigation, and you drive from here to Phoenix and you see alfalfa and cotton being grown, which are very water intensive. We grow alfalfa in my other home in Vermont, which is wonderful. We get a lot of rain, but it doesn't make a whole lot of sense. And so I'm wondering, what is the state doing to conserve water in the farming areas? Because we also have open irrigation ditches that run, along the way from here to Phoenix, and that water will evaporate. And you're growing fruits and vegetables in areas that are just purely desert, and the only reason we're able to do that is because we're irrigating them. But at some point, that's really the biggest chunk of water use is irrigation for farming. And I know there's a huge farm lobby and all that, but it seems like the state has to get a little more serious about what it does for water use in farming. As the Arizona Republic expose on the area from Saudi Arabia that's drawing down the aquifer in that particular part of Arizona. So I guess that's really kind of it. We're 6%. The other bigger number is the farming. And so I would say that, as a part of what your office does, you need to really evaluate what the future of that is over the next 100 years rather than, the 6% here. This is a small portion of the actual water use.
And I thought my question was political.
You make
I'll give you credit for it.
you make very, very good points. It's above my pay grade. Obviously, it takes.
But maybe you can take it back to your higher pay
I
guy.
guarantee you, they hear it all the time. I can guarantee you they hear this all the time. A lot of the agriculture, a lot of it's economy-based too. Like if they have to start pumping water that's 1,000 feet down, that's a lot of power. So it's going to come down to, are they making any money? And we've seen areas where they had to stop farming in like the 60s, 70s, and 80s in Arizona because it was too expensive. And we saw water levels recover. There's not much going on there now, or as much. But yeah, you make very good points. That's all I can really say.
Gentleman over here, stand to his hand.
Go ahead, yes.
No, you. Yeah,
Which one?
the red.
Red.
Yeah.
Okay,
Right.
hey, here's a fun one for you. I've got some property that's got 1864 water rights. Does that give any special rights?
Where's it at?
It's in Oregon. Let's say that 1864 water right was here in Arizona. Would that give me first dibs to my water?
You would have what they call a grandfathered right, yes. If it was in an active management area, yes.
So I would have rights over the farmer just moved in like 2 years ago or 10 years ago.
I believe so, yes. So that's one part that I'm not fully versed on is the grandfather right part.
So these farmers, if they've had their farms for 200 years or 150 years here, don't you think they would have water rights over the people who just moved in now from California?
But potentially, but I don't know what the law is, what the regulations are on that, so the rules. So I can't really speak to that. I'm sorry. Yes, sir.
You talked a little bit about desalination. That's a very, very, very expensive proposition.
Oh, yeah.
I would think every year we we hear about the floods that take place in the Midwest, Mississippi. Has anybody ever looked into the possibility of pumping water from the Mississippi basin towards us to refill our aquifer?
Right. We all have heard, stuff about that, but that's an expensive proposition too. You know how much power Central Arizona Project uses to lift water from pretty much sea level to Tucson?
A lot less than desalination.
Possibly, but that's talked about. It's definitely a possibility, but then you're talking about different water chemistries and things like that.
Back in the back there.
If we're replenishing the aquifer by basically pumping water into it, two questions. Where does that water come from? And number two, if it's being pumped into the aquifer, isn't there a chance that we're pulling it back out in a relatively short amount of time so there's no percolation of that water?
So, what was your first part again? Where does it come from? So it can be treated wastewater, effluent as we call it.
Is that where it comes from?
Yeah, a lot of it is just your treated wastewater that they put in surface basins, settling basins, so it naturally gets purified even more as it percolates down. And they put these in areas that have usually more coarser grain material, so they'll percolate down much quicker. And then the second question was.
I thought we were pumping water.
Yeah, we don't pump it down. There is something called an ASR well, an aquifer storage recovery well, where it's put down right down the well casing in the winter, and then but that's not treated effluent. That is Colorado River water, and then it's recovered later on. But what we've seen with those is that you don't get the larger declines that you get if you weren't doing that. Yes, you still get some decline, but it's not as much because you're recharging the aquifer and also recovering. So you're kind of balancing it out, like making a deposit in your checkbook and withdrawing it.
Yeah, there's a lot of conversation. I've lived in Arizona for 20 years now, and there's a lot of conversation with this 100-year water supply guarantee. Every developer, they're building thousands of new homes in the Prescott area by the minute. They're building in Tucson. Everybody wants growth. I believe the government can't be honest with us because of the growth issue, the political issue, the tax issue on a water shortage basis. Can you address what these people know that we don't know that are guaranteeing a 100-year water supply? If they did, there wouldn't be anybody in this meeting if everybody thought there was a 100-year water supply.
Well, they're basing the 100-year water supply off a groundwater model that has assumptions in it.
Isn't there a lot of unknowns about the amount of water that we really have underground?
We have quite a bit of data that, we have a pretty good understanding on how much water is available, how quickly it drops because we take measurements, every year and all that stuff. And so all that data is input into a model. They do calibration testing on it and all that stuff. And you look at error analysis, and if they see there being high errors in the error, in part of the model, they go in and try to figure out why to improve it, basically.
I guess the follow-up on that would be that I'm under the understanding that we ought to be dealing with conservation, reservation, or reservoirization of the water rather than taking it out of the ground. Because once our groundwater is depleted, that's it, folks. It's like the Indians 5,000 years ago. Moved to Mississippi for water. It's going to be the end of our water supply at some point in the future with all the growth and the political situations and the lack of people being active in conserving water at the agricultural level, stopping Saudi Arabia from growing their alfalfa here, et cetera, et cetera. I don't understand why there was more water restrictions in Georgia when I left 15 years ago than there has been in the 15 years I've lived in Arizona, and it blows my mind.
But what Brian has just told us is that there is a 100-year guarantee, and I know you're not agreeing with him, but he did say that.
Well, then
he said that
why are we having this meeting?
He also said their models. He said their models are proving the fact that there is a 100-year guarantee there.
Question about that. Did they take into account a worst-case scenario on this 100-year water supply, assuming the worst-case scenario is in terms of drought? Is that plugged into
They
the
have
formula?
different assumptions that they put in there.
Okay.
Yes.
You mentioned the farmers and they, they're getting water cutbacks through the Colorado River supply, stuff like that. Once they start pumping water out of the aquifer on their farms, do they have to pay somebody for that water? And who do they pay?
So if it's an active management area, they have a withdrawal fee for a certain amount for each. I don't remember if it's an acre foot or how many gallons, but yes, they have to pay withdrawal fees.
And who gets the money?
ADWR, well, the state gets the money, and then it's used for projects within the active management area, whether it's conservation or whatever.
What if it's
The
outside?
Groundwater Users Advisory Council for each AMA decides how that is being used.
If it's outside one of these management areas, do they have to pay?
Nope, there's no withdrawal fees or anything like that.
How much?
Just one question on the 100-year plan. I'm assuming that we show where SaddleBrooke as an example, or we're recharging in enough water to support the 100-year withdrawal. Does it have to be recharged into the same area? Or can I say, I'm buying in SaddleBrooke and I'll recharge it in Arizona?
Yeah, that's, so the recharge, a lot of times it happens not where the water is being withdrawn, just because of infrastructure and the geology. But there are other areas where they do recharge close to where they are withdrawing it.
You have several Indian reservations in Arizona. Are they immune from any regulation regarding water usage?
They're their own sovereign nation, so they get to do what they want. Yes.
Does the 100-year model assume equilibrium of the water level, or is it assuming a final depletion level?
It varies by active management area. I think Tucson, and don't quote me on this, I think it's 1,000 feet below land surface. So it's not like it's going dry, but the water level can't drop below a certain elevation for that AMA. I can't remember what it is. I want to say it's 1,000 feet for Tucson, but don't quote me. Yes.
How much of the agricultural area is outside of the AMA management?
I can't really answer that. I'm not sure. I'm sorry. If I had to guess, maybe 50%?
Would you explain how the model was used to impact development in the canal active management area for those?
Yeah, I'm not a modeler, so I can't really answer that. I'm sorry. Yes, ma'am?
On average, how deep are the wells in the SaddleBrooke area?
I think they were, well, how deep do they go? I'm not sure. I'd have to pull up the well log information to see for that. Yes.
Am I clear in understanding that you really don't know the size of the aquifer that we're getting our water from? And
I mean, when you're in the model, you can get someone, we can't see on the ground, so you can't see how deep the water really goes. Unless you have a well that goes all the way down to bedrock and it's screened, all over the place. It's hard to be able to understand those things.
So one of the things that make people not believe the 100-year situation is that we don't actually have monitoring wells in SaddleBrooke. They're around SaddleBrooke. And so in interviewing the Lago del Oro staff, I found that they say that they report to the state how much water is used by the utility, but they do no static well monitoring because the wells impact each other.
Right, yeah, so in any non-exempt well, which is anything that pumps over 75 gallons per minute, I believe, has, in an active management area, has mandatory water metering that you have to report to our agency. So all the water providers, farmers who are AMAs have to provide their water usage to us.
So that's what gives us the line item on our property taxes for replenishment in the replenishment district.
Yeah, I'm not exactly sure how that works, but and also that water use is used in the modeling as well, because we know exactly how much everyone's using.
Right, but the fact that the monitoring wells that the state uses are not in SaddleBrooke proper, where the production wells are,
right,
is what leads this question about whether we have 100-year water supplies, because we don't know how well connected our aquifer under us is with the aquifer that is in those monitoring wells around us.
Yeah, I also talked to the Del Oro management group, and I asked them what water restrictions or what our future looked like with all the cutbacks and all the drought and all the conversation that's going on. And their answer was reasonably honest. They said, look at California. That's a predictive future for Arizona as far as restrictions, limitations, problems. What's your take on that? And from an Arizona standpoint, let's talk about the future. We obviously have to do something if the rain continues to fall at a lower level than we restore our groundwater. So please address the future. 5 years forward with the same weather conditions that we've experienced for the last 20 years, what is our contribution and water reduction or usage look like or projected to be?
Well, I can't really predict
I didn't say predict, I said using the data from the last 22 years, which is reasonable considering what we're going through, and nobody's predicting it to change. If it continues, what contingency plans are in place for us to contribute or be restricted for water price increases or water usage decreases in the future?
Well, population growth.
That's outside my area of expertise. I can't really.
You must know from an interagency conversation standpoint at the water cooler what is going on. What's the thinking?
But the point is, he did show that the rain levels are remaining consistent. They're not decreasing. So he showed you what's happening with the recharge of our thing. The rain levels are staying consistent.
Every
In fact,
article
some of them are
read
going up. Excuse me?
It talks about well water or groundwater. I have never read an article where it says the groundwater is going up. The well water was, hey, 160 feet last year to reach water. It's 230 feet down now to reach water. The water under the ground seems to be going down a lot faster than
You're asking a
water.
question where he showed you that in fact the rainwater is staying consistent.
That's fine, but it's not enough to sustain us.
We don't know that. We have been told that it is.
Then why are we having this meeting and why is everybody concerned about the water in Arizona?
Yeah, no, I think he's answered those questions pretty well.
Because the media is.
I mean, I was asked just to come give a presentation about hydrology. It wasn't anything about the 100-year assured water supply, because that's not my area. I'm not in the assured and adequate water supply section.
You've had enough of these conversations and seminars, I'm sure, to get the same questions over and over. And I'm sure this conversation.
Most of my presentations are about subsidence.
Are there other